We are now on two dimensional plane groups. We have not yet reached the plane group. What we have discussed is 10 two dimensional point groups. So, that should be all clear to you by now, that in two dimensions the only point groups, that is only symmetry groups which will leave one point unchanged, will be 1, 2, 3, 4 or 6, and the corresponding versions with mirror. So, m, 2 mm, 3 m, 4 mm and 6 mm. You should now be familiar with the reason why we write double m's in the case of 2, 4 and 6 and a single m in the case of 3 and 1. 3m also has 3 mirrors, but those 3 mirrors are equivalent to each other by the threefold rotation. 4 mm has actually 4 mirrors, but not all 4 mirrors are equivalent to each other by fourfold rotation. So, 2 of them are equivalent to by fourfold rotation, another 2 are also equivalent by fourfold rotation, but one pair of twofold is not equivalent to another pair of twofold by fourfold rotation. So, we want to show those pairs. So, each m in 4 mm case, each m is actually representing 2 mirrors which are equivalent by fourfold rotation, but another m represents another 2 mirrors which are not equivalent to the first set of 2 mirrors. So, we have seen these things in the previous class. We will again revisit them later. After that we were, so since it is point group, so one point is left unchanged. So, automatically translations are not allowed. So, in all these combinations, the mirror plane and the rotation, we are looking at symmetries which will leave some points unchanged, and in the case of 2 mm, 3 mm and so on, where you both have rotation axis or rotation point and mirror, they should all pass through the same point to leave that point unchanged. So, translations are not allowed, there is no translations here. Because translations, translations cannot leave any point unchanged, it will always shift. But when we are talking of periodic patterns, translations become important, and it is translations which give you the periodicity. So, then we have to look at how many different kinds of translations are there, and that is characterized by lattices, because lattice actually gives you the set of translations through which this periodic pattern will come into self coincidence. So, that we claimed that there are 5 types. We met 3 of them in the previous lecture. So, the way we were doing it was that we were trying to see. So, these 5 types are also again by the symmetry which these lattices will have. So, if lattice has no symmetry, and we saw that it is not possible for a lattice to have no symmetry at all, because every lattice has the twofold symmetry, because for every lattice translation. So, if we call this a translation A, then minus A will also be a lattice translation which will take you to some other lattice point. Similarly, if you have this as B, then minus B will be also a lattice translation which takes you to another point. So, each lattice point itself becomes an axis of twofold. So, this is anyway guaranteed. So, this is the minimum symmetry which any lattice can have, and we call that this kind of lattice the oblique lattice. So, there is no relation between A and B. So, the lengths of A and B need not be equal, and there is no relation, no particular restriction on angle gamma. Gamma can be any arbitrary angle. So, even with non-equality of A and B and even with arbitrary gamma, the twofold anyway will emerge. So, that is your minimum symmetry lattice and has been named oblique lattice. Instead of twofold, if you have, let us say, some other symmetry, if you want to endow your lattice with some other symmetry, some other interesting symmetry, let us say. So, apart from twofold, what other symmetry you can give to a lattice? So, let us give a lattice a fourfold. So, let us begin with a lattice point and let us make that lattice point an axis of a fourfold axis. Now, of course, since you have a two dimensional pattern of lattice point, we are talking of 2D lattices. So, there will not be just one lattice point, there will be other lattice points. So, as soon as you have one more lattice point, you know that by translation you will have entire row of lattice points both in the forward and backward direction. But that will give you still a one dimensional lattice, it is giving you a one dimensional lattice. If you want to have a two dimensional lattice, you will have to have lattice points in other directions also. But now, since you are you can have it in any direction, but since you are insisting that the lattice point is a fourfold axis of symmetry, then whatever this lattice translation is there, this will rotate by 90° to generate another equivalent lattice point there. Unless and until you do that, this fourfold symmetry will not be there. So, the fourfold symmetry itself forces that you have another lattice point at 90° to a given lattice vector and at the same distance, because this, since this is a rotation of this vector, the two vectors will have the same length. So, although we call one of them, let us say A and another B, we now know that A and B cannot be arbitrary. If I want fourfold, A and B should be of the same length, and the angle between A and B is gamma. Gamma also is now no more arbitrary, gamma has to be 90°. So, these two constraints are there on the lattice parameter if we wish to have a fourfold axis. And of course, all lattice points, since one lattice point is a fourfold axis and all lattice points are equivalent, we know. So, all these lattice points will have fourfold axis of symmetry. So, obviously, you have now what is called a square lattice. However, the symbol is chosen as tetragonal P. Tetragonal is a 3-dimensional lattice where A equal B not equal to C. Here there is no question of C. Still, in the international convention, maybe to relate it with the 3-dimensional lattices, this will be one plane of tetragonal lattice, the basal plane of tetragonal lattice. So, the 2D lattice also is given the name TP, and I am making a mistake here. So, let me correct myself, because that is what I told you last time also, that is what distinguishes the notation from 2D to 3D. In 2D we will use a small p, in 3D we will use the capital P. So, TP will be a square lattice, whereas T capital P will be actually a tetragonal lattice in 3D. So, it is not just equality of the lattice parameter and the angle of 90 degree. We see that if we have this equality and if the angle is 90 degree, the lattice is actually endowed with a different symmetry. So, oblique lattice where it was having only two-fold, now with this constraint on the lattice parameter, it has become a four-fold axis. So, it has a different symmetry, and that is the reason why we want to call it or count it as a different lattice. So, four-fold we have given. Now what else you want to give? Threefold. Why not threefold? So, suppose you have threefold, do the same analysis, have a lattice point on the threefold and have any other arbitrary lattice point. Now, this distance can be arbitrary, but now our insistence or our requirement that I have a threefold axis in my lattice or in my pattern, I know that this translation has to be rotated by 120 degree to generate a threefold. So, in other direction again by 120 degree. So, again you see that threefold is also demanding that A and B are equal, means you can write it as modulus of vector, or you commonly write simply without the vector sign A equal B, but now gamma is equal to 120 degree. Of course, you can generate, once you have two lattice points which are not collinear, you can generate the entire lattice simply by vector additions. You will keep getting other lattice points. So, this will be your unit cell. All lattice points are identical, so all lattice points will be threefold. Of course, more symmetries will get generated, we will look at that, but currently we are simply stopping here. So, this we could have called a triangular lattice, but we call it still a hexagonal lattice. We will see the region soon. Sorry, I also need practice to remain in two dimensions. So, HP. You can consider sixfold, or we have considered twofold, threefold, fourfold. The only axis now remaining, rotation axis, is the sixfold. So, you can try to construct a sixfold lattice also. So, sixfold will require a rotation by 60 degree. Now, you see that you have also generated, joining any two lattice points you get a lattice translation. So, you have also generated, let us say, this green lattice translation, and if you start that green lattice translation from your original point, then you get another lattice point here. So, if you now call this green one as A and this as B, you see actually there is no difference between the lattice which you created by a 60 degree rotation and a lattice which you created by 120 degree rotation, because here also when we created the lattice, you did not notice, or we did not highlight, maybe you noticed that there is a vector at 60 degree. So, a lattice generated by a 120 degree rotation, that is the threefold, and a lattice generated by 60 degree rotation, which is the sixfold, are actually the same lattice. And that was the reason why the triangular lattice was also called a hexagonal lattice, because actually it is the same, and this also we call a hexagonal lattice. So, sixfold and threefold give you the same lattice. So, although we were calling it threefold, from the point of view of lattice, if you see, that will become all the points are actually sixfold, because there are 6 vectors around any lattice point. So, if you focus on any lattice point, you can see that lattice has 6 neighbors surrounding it. So it's really not a threefold axis, it's a sixfold axis. But does that mean that you cannot have a pattern with threefold axis? Because if you are trying to create a threefold lattice, you are getting actually a sixfold lattice. Same thing, same issue was there in this oblique case also. Can you not have a pattern without any twofold rotational symmetry? Because when we tried to create a lattice without twofold symmetry, we found that we are bound to find twofold rotation. So, that is where the difference between lattice and the plane group comes. In the plane lattice, yes, in a plane lattice you can never avoid twofold axis. In a plane lattice you can never have threefold, you will always have sixfold. But you can have patterns with threefold symmetry if you start putting objects only with threefold symmetry at these lattice points. So, that is the motif. So, threefold axis in a pattern will come from the motif, not from the lattice. Similarly, if you put in an oblique lattice a pattern without twofold symmetry, a motif without twofold symmetry, then you will destroy the twofold symmetry of the lattice and you will get a pattern without twofold symmetry. So, those things we call as different plane groups based on the same lattice. So, rotationally you saw that in terms of rotation, if we look at rotationally different lattices. So, we have oblique, then we have square, and we have hexagonal. Oblique, I did not give you the symbol. So, oblique also should have a symbol. I am little doubtful about it, but let us for the moment I think we can check this. Probably it has a symbol A. So, AP, TP and HP. Question mark for a little bit of doubt I have. Then we saw last time in these cases we are not thinking of mirrors. So, mirror gives us two rectangular lattices. So, we saw that there was a primitive rectangle and rectangular lattices were given the symbol orthorhombic. So, orthorhombic primitive and orthorhombic centered, OP and OC. So, we have completed these 5 lattices. Only these are the possible symmetries which are possible, because we saw that only 2, 3, 4 and 6, these are the symmetries, rotational symmetries. So, 3 and 6 gave you the same hexagonal symmetry, 4 gave you the tetragonal and 2 gave you oblique. Similarly, if you have the mirror, then you can have M or you can have 2 mm. These will come under rectangular. If you have 4 mm, so that will come in a square. Well, this classification way of writing is not looking good to me, because I said rotationally different lattice and this is lattices with mirror, but 4 mm is also with mirror. So, probably my heading is not justifying what I am writing. So let me cross out the heading for the moment. Just look at just let us distribute the 10 point groups. So the heading should be 10 point groups associated with 5 lattices. I think that seems more reasonable. So 4 mm will go to a square, then 3 mm and 6 mm, these will come to hexagonal. So I think we have now all. One is oblique, so that will go there. So we have all the 10 point groups now. So 10 point groups and 5 lattices. Hexagonal lattice has 4 different point groups, supports 4 different point groups. A square supports 2, oblique supports 2, and rectangular also supports 2.